Okay. Good morning, everybody. So we're gonna jump back into the exponential stuff. If you need a copy of notes from last time, there's some here. Quick recap version of what we did Tuesday. Started talking about exponential functions. Again, exponential is the idea that you've got a fixed base raised to a variable power, right? So if we're talking like taking, full steps or evaluating like integer values of x, then we're talking about multiplying, over and over again by a copy of whatever that base is, right? So 2 to the x is, 2 times 2 times 2 times 2 x times, right? It's a continuous function, so it's connected. So all of the like in between stuff is there too, where, it's hard to make sense of what it means to multiply by, 3.7 copies of 2, but like that stuff's there as well. But the like nice integer values would be, power to 2 basically. Pretty much the idea is that if that base is bigger than 1, then you get something that, is increasing over time. So it looks like that. So we call it exponential growth. So the difference between like 2 to the x and, 3 to the x or something would just be that 3 is going to do the same thing, but a little bit faster. But it's going to be the same basic idea. They're talking about exponential growth. The flip side of that would be that if the base is smaller than 1, like 1/3 or something, then instead of growing over time, it's going to decay because it's a decreasing function. Because if you multiply something by 1/3, you get back a smaller thing than what you started with, and here you're doing that over and over again. Same stuff applies in terms of the domain and the range and horizontal asymptote and intercepts and all that kind of stuff, right? Now, I did mean to mention, we talked about like the horizontal asymptote, the intercepts and all that stuff last time. If you take one of these and start shifting it around though, right, everything else moves along with that, right? So this doesn't have any x-intercepts sort of on its own, but if you took it and shifted it down or something, well, now it does because it's, moved that asymptote along with it, right? So I just didn't want to, be misunderstood there. So if you haven't gotten into it already, the homework on this stuff where you're graphing, the graphing tool in MyMathLab, it sucks anyway, but like it kind of it does a couple of weird things with the exponentials. You have to like tell it what the base is, and then you like do the shifting thing. So just watch out for that. Sometimes it'll like if you open it, it'll have the correct base set already. Sometimes you have to manually change it. So just sort of be aware of that, and then when once you actually figure out what it's asking you for, it's actually a little bit easier to use than some of the others because you just tell it how you want to shift. But if you're not sure what it's asking you to do, then it's kind of frustrating to work with it. As always, though, we're just going to sort of get through that part. Okay, and then the other thing that we talked about is these compound interest formulas. These two formulas, again, for compounding is happening periodically or continuously. I'm going to give you those formulas on a test or whatever. I'm not going to have them labeled, and you got to know what everything is and when to use each one. But I'm going to give you the formula part, so you don't need to worry about trying to memorize that. Probably by the time you get there, you'll have done it enough times that it won't matter anyway. But I will have those for you on the test or whatever. So again, the kind of what everything means. A is the amount now or like after time has passed. P is the principal, so that's the starting or the initial amount. That's how much you borrowed or invested in the first place. R is the interest rate. T is time in years, and then here where N shows up, that's how often the interest calculation happens. So I think if I remember right, we set up at least the first one on Tuesday, and then I said like do the rest of them. So let's just go back through this real quick. $1,000 invested in an annual interest rate of 4%, compounded quarterly, which means 4 times per year. We want to know how much will be in the account after 10 years if no withdrawals are made. So basically, like if I don't take anything out or put anything else in, I just take $1,000, put it in the account, let it sit for 10 years. What's going to happen? So the first thing is that compounding quarterly. Quarterly means 4 times per year. That means it's happening sort of every so often, right? So that's this first formula, the periodic one. If we're meant to use this one, like you would actually see the word continuous in the problem somewhere about the compounding schedule. Otherwise, it's this. So compounded quarterly, 4 times per year, that's in. $1,000 is the principal amount, 1 is 1. Interest rate is 4%. Again, to use that though, we got to convert it to a decimal. So 4%, slide the decimal over 2 places or divide by 100, that's 0.04. And then 10 years, so T is 10. If you haven't already, which you should have, but if you haven't already, grab your calculator, punch all that in, and then tell me what you get. Somebody already have it? 14 something. 1488 and how much? 86. And we know it around to 2 places because this is money, right? That's a dollar amount. So 2 places for cents. So again, like verify that you get the same thing in your calculator. There are a bunch of places where, depending on like how you got to enter stuff, where things can go wrong here. I threw a little set of parentheses around this. You probably want to do that 4 times 10, first, or put it in parentheses or something to make sure that it does 40 as the exponent, rather than if you type things in a way that's not careful, it'll do this whole thing to the 4th and then multiply by 10, which is a lot different than doing to the 40th power. So just verify that you get that. Once you've done that, try to set up 10 and 11 also. If we get on the first one, then they have like calculator questions or where did I go wrong or whatever. This will be another place where, like, if I ask you a question like this on a test, make sure to write this step out. Like, don't just jump to, because like you're going to get to the point where you can probably go directly to the calculator. So write this step out, because if something goes wrong, that way I can tell that like, if you did all the right stuff and this is wrong, I might take a point off. I might even not do that if I'm in a particularly giving mood. But like this is going to get you most of the points, because I can see like the right thing, you put stuff in the right places. Okay, so what's the setup look like on 10? What's different? Same investment, so same principal amount. The account still pays 4% interest. We're still talking 10 years. What's different though? Compounded monthly instead. What does that change? N is 12 instead of 4. And what do you get there? $90.83. Again, these are all dollar amounts. Okay, so what do you notice? Interest rate was the same, time frame was the same, amount of money I started with was the same. Interest calculation happens a little more often, and we ended up with a little bit more, right? Not a lot more, a little bit more. Generally, the idea is when you do that interest calculation, it's okay, what's 4% of what's in the account? Okay, add that on. The annual interest rate part is that it's 4% per year. This R over N thing is that you're taking that 4% and breaking it up and doing it 4 different times, right? Or here you're doing 12 different times. But every time you do that interest calculation, it's a little bit more, the percentage is a little bit more than the time before, right? Because you figured the interest and added it on. So the more often you do that, the quicker, things sort of accumulate. Again, it doesn't make a huge difference, right? A little less than $2 here, but it, is a little bit more. Okay, what about the last one? What's different there? Continuous compounding, which means use the other formula, right? So A is, how do I need to set that up? What's P? 1,000. Continuous interest formula is P times e to the RT, so E is E. Interest rate is still 0.04. Time is 10. Again, this would be another place where you just want to make sure that that multiplication happens before the exponent does, right? So 1,000 times e to the 0.4 or e to the, root 0.04 times 10. And what do you get? Probably a 1. $8.2. Okay. Continuous compounding. So that's like, instead of doing this once a month, we're sort of treating it like it's always happening, right? So it's not so much like go in and do the calculation as like, okay, it's just sort of always running. This is where, and again, I'm not going to get into the details because in calculus, but if you go on to calculus, this is where E actually comes from, is taking this thing, sort of letting stuff, be certain values, but letting n go to infinity, doing a thing that we call a limit. That's the definition of E, so that's why, the thing does what it does. But again, notice that if everything else is constant, nothing else changes except how often we do this, then this gives you sort of the most, right? And that would be like the cap on it. So if you did, if you did this once a year or something, it would be kind of up here, right? A little bit less. If you did it every day, it would fit in here somewhere, kind of in the middle. But continuous is like, sort of every moment in a sense. So that's the cap on the thing, the ceiling. Okay, kind of make sense? Okay. So if you're comparing two things, and you'll see some stuff like this in homework and other places. I think there's one of my notes somewhere. Where it'll say like, okay, what's better to do this at like 3% monthly or like 2.8% continuously? Well, continuous means more often, but the interest rate's a little bit lower, right? So to compare those, you would just like calculate them both and see which one gives you more, right? Okay. If the interest rates were the same, like here, 4%, well, quarterly is going to be less than monthly, monthly is going to be less than continuous, right? If the interest rate's the same. Okay, cool. So again, yeah, that's one application that we'll come back to a couple of times as we sort of figure out more about how we work with these things. Like right now, pretty much all we can do is plug everything into the formula and press enter. When we figure out some more stuff, we'll be able to solve and answer things like, well, if I had this much money now, how long would it take for me to get a certain amount? Okay, so we'll come back to that. All right, so the other thing that we can do for right now is solve some equations. Like look up at the top of the page there on the back. We can solve some equations using just what we know about how exponentials work, right? 5 to the x, you can think of, at least for like nice x values, as being just, a bunch of copies of 5 multiplied together. So if I want to figure out something like when is 5 to the x equal to 25, we can use what we know about the base here, 5, and the number here, 25. Well, that's not just anything, right? Those are related, right? What does 25 have to do with 5? $25 is 5 times 5, right? Or it's 5 squared. So what this question is asking is, when is 5 to the x equal to 5 squared? When do you think 5 to the x is equal to 5 squared? when x is 2. And you'd be right. This is because exponentials, again, have the picture in mind or the graph. That's 1 to 1, right? If a function's 1 to 1, then you can undo it. You can answer a question like this by doing the thing that seems obvious, right? If 5 to the x is equal to 5 to the 2, well, x has got to be 2, right? That's the only way that that would work. Again, because it's 1 to 1, I can say that. So if I can sort of, like cleverly approach the thing and figure out a way to look at both sides in terms of the same base, then we're good to go. We don't have a problem. So, maybe take just a couple of minutes and think about like maybe the first 3 there, 1, 2, and 3. Take a minute, see if you can, think through how you would solve those with the same kind of approach. Okay, so how can I write 32 as a power of 2? Yeah, 32 is 2 to the 5th, right? And if you're not sure, you can just, start multiplying 2 by itself and count, right? 2 times 2 times 2 times 2 times 2 again is 32. So this is 2 to the 5th, which means that x must be 5. Okay, and similarly, 81 is 3 to the 4th, which means that x must be 4. Okay, that's all right, cool. One moment, technical difficulties. Okay, all right, cool. Okay, so, just 81 is 3 to the 4th, 3 to the x is 81, that means x must be 4, right? A little bit more going on here. 27 is 3 cubed, right? So that means that this must be the same as this. And if x minus 1 is 3, then x is 4, right? So we just have something else to do after that. Yeah.
What's that little sign?
Oh, just like this implies that. So I'm just using that to like sort of go to the next step. So if these two things are going to be the same, the only way that can happen is if these are the same, right? Because again, it's a one-to-one function. So yeah. What is happening? Now the Zoom thing will have broken. Okay. That's not the right thing. Now we're back in business. So it implies, so it's like an if then, right? If this is true, then this must be true. Okay. What about something like 5 to the x equals 1 over 125? Well, we kind of get into like, a little bit like things that might not be quite as recognizable as, like you might not know that 125 is 5 cubed right off the top of your head. I promise in a few minutes, we're going to have a better way to do this anyway, right? Than just sort of guessing and hoping that we, land on the power of the thing. 125 is 5 cubed though. So 1 over 125 is 5 to the negative 3. So again, then this must be the same thing as that. Okay. And the same thing's true for, something like this. We could even think through that, because what do you know about 3 and 9? 9 is 3 squared. So 3 to the 4x is equal to 3 squared to the x plus 1. Well, how do you raise a thing that has a power on it to another power? Think about, I don't know. If it was 3 squared cubed, that means to take 3 copies of it and multiply them together, right? But each of those 3 squareds is just 2 copies of 3. So total, we've got 6 of them. And the faster way to get to 6 than writing all that out would be to take 2 and 3 and multiply, right? So power raised to another power, you multiply the exponents. That's how you combine them. Because of how exponents work and because how we're using the sort of shorthand multiplication. So you multiply, which means this would be 3 to the 4x equals 3 to the 2x plus 2. Why? Why is this happening to me? I feel personally attacked. People who are watching the recording later, all of my stuff is breaking, and it's not my fault. Now I don't even know where we were. Here we go. So again, then this would be the same as that, right? And you would just solve from there. So if we can, and if you look at the textbook, it calls these type 1 exponential equations. What it means by that is just that things where you can, if we sort of think about it enough, figure out how to look at both sides of the thing in terms of the same base. Now, again, that only works if that happens, right? If that works. So look at, let's go back to this first one, 5 to the x equals 25. The reason I'm able to solve that is because 25 is a nice power of 5 that I can guess, right? Or that I recognize, that I know already. This would not work if I wanted to solve something like 5 to the x equals 20, right? 20 is a power of 5. It's just not a nice one that you're going to guess or do by hand or, for multiplying by 5 a bunch of times, right? It's, think about 5 to the x. Its range is everything from 0 to infinity, right? So it passes through all y values. Think of this like a y value, all positive y values, sorry. So it hits this somewhere. If I think about it a little bit, it's going to be between 1 and 2 somewhere, but I can't really get more specific than that, right? So this has a solution somewhere. It's just that I can't sort of guess it or clever my way through it like we can here, because 20 is not a nice power of 5, right? So what we need then to handle this kind of thing, or to make what we're doing with the rest of these a little more automated, right? So that it's not just a matter of me being clever enough to recognize that something is a power of the base or count up to it or whatever. This is all a lot harder if it's 3 to the x equals 2187, right? That's a power of 3. It's just 3 to the I don't know, 7th or 8th or something like that. And like, that's not one that I know off the top of my head, right? So like you could do the same thing there, but like it doesn't jump out at you the same way that maybe this kind of does. Does that make sense? Sort of smell and cooking. All right, so we need some way to undo exponential things so that we can solve stuff like that, which has a solution, and like there's no reason that we can't find it, except that we don't have the tools yet. And that tool is a thing that we call a logarithm. Again, the kind of like motivating idea is that we need a way to undo this exponential. Anytime that we talk about undoing a thing, we're talking about inverting it, right? Finding its inverse. So, you know, for a cube, the undoing is taking a cube root because that's the inverse of that operation, that function. So we're trying to do the same thing here, right? That's what a logarithm is. So logarithms do the same thing as exponentials, they just do it backwards, right? They, you know, think about a function, its inverse. They take x and y and swap how they work, right? So they give you the same information, just in kind of backwards order, right? Just like if I say that, you know, 2 cubed is 8, and the cube root of 8 is 2, that's, for heaven's sake, what? All right. Okay. 2 cubed is 8, the cube root of 8 is 2. Like this is kind of, in a sense, the same information, just like backwards, right? Just in reverse order. So it's the same kind of thing with exponentials and logarithms. If exponentials tell us like how much a thing grows over a certain amount of time, like we did the zombie apocalypse thing last time, and we answered questions like, okay, after a week, how many zombies are there? After a month, how many are there? So what we're doing is giving it a time value, and the exponential thing is telling us how many there are, how much it's changed, how much it's grown. The logarithm would answer questions like, well, how long would it take to grow by this much, right? The logarithm is going to tell us like, okay, this is how much I need or want to know about. How long does that take? That's what the logarithm does. Okay, so here is just a statement of a fact, right? 2 cubed is 8. 2 times 2 times 2 is 8, or 3 copies of 2 gives you 8. The way that you express that same idea as a logarithm is this. The log base 2 of 8 is 3. Or the base 2 log or whatever. But the subscript here, so that 2 is a subscript, you know, a little 2 sort of hanging out in the middle of the line there. The log base 2, that tells you what kind of logarithm you're doing, right? So it tells you about the base the same way that the base works here, right? This means that the thing that we're looking at is multiplication by 2. On 8, well, this says the log base 2 of 8 means how many copies of 2 are in 8? Well, how many copies of 2 are in number 8? 3, right? How many steps, how many times do you have to multiply 2 together to get 8? Well, 2 times 2 times 2 is 8. So the answer then is how long it takes. So that's what the power is, right? It's 3 steps or three times of multiplying 2 by itself to get to 8. So does everybody see how that's kind of the same information, just backwards, just flipped around? All right. So 3 to the 4th is 81. There's another thing. How would you write that same thing as a logarithm? If the base here is 3, then the base here is 3. And then the things that work like X and Y are like the input and output, just swap places. So here, if I'm thinking about an exponential function, 3 to the X, I'm taking the X value 4, and that gives you back 81 when you plug it in, right? Because 3 to the 4th is 81. For the logarithm, then, we just swap those. So the log base 3 of 81 is 4, because 81 is 4 copies of 3. Or 4 steps of multiplying 3 by itself. 3 times 3 is 9, times 3 again is 27, times another one is 81. Does everybody kind of see how that works? Okay. If you can do this thing, go from this to this in either direction, and even if there's an X in there or something somewhere, this is going to be, I think I said something last time about there being sort of one big like central idea that kind of holds all this stuff that we're going to do in chapter 6 together. This is it. An exponential is multiplying it by the same number a bunch of times and sort of counting that up and seeing what happens. A logarithm is flipping that around and seeing how many times you would have to do it to get to a certain place. But if you can go from one of these to the other one, that's going to end up being sort of the key step in basically everything that we're going to do, right? At some point, whether we're working with a function or solving an equation or whatever, at some point we're going to end up going from one to the other, and like ta-da, everything's going to sort of work itself out. Okay. All right, so y'all work on the or tell me about the next couple then. Five to the what gives you 25? 2, right? 5 squared is 25. How do you write that same, fact as a logarithm? That same relationship. It's a log base 5 of 25 is 2. Yeah, good. Okay. 1/16. We've got a negative exponent, right? So what to the negative 2 power would give you 1/16? 4. Negative means you're going to flip it over. 2 means you're going to square it. So if we take 4, flip it over and square it, you get 1/16. What does that mean as a logarithm? The log base 4 of 1/16 is -2. So again, base, answer, and exponent. So write answer like that because it's like the answer, the outcome of doing the exponential thing. For the log though, it's the thing that you take the log of, right? And what that gives you back back is the exponent, right? So the answer to a logarithm, like what a logarithm gives you is a power, right? It's an exponent. Okay, square root of 49 is 7. So the log base 49 of 7 is square root, right? So what's a square root as a power? Square root means you take the thing and break it into 2 equal pieces. Logan, what you got? So it's a 1/2, right? Okay, and the last one, 3 to the what gives you 1? 0. So the log base 3 of 1 is 0. Okay. Does the fact that the base was 3 here matter? What's anything to the 0 power? 1, right? So the log with any base of 1 would be 0, right? Okay, so we're not going to get into like the graph of a logarithm yet. We'll do that tomorrow. But exponentials look like this. Logs are their inverses. Well, exponentials all have, remember all the ones we looked at the other day, they all cross the y-axis of 1. Because anything to the 0 power is 1. Well, logarithms, the same thing is going to happen where no matter what the base is, if you're talking about the log of 1, you're always going to get 0. That means they're all going to have a x-intercept in the same place, right? And it's just going to be a question of kind of the same shape, but different amount of like how steep it is. Are we all right with stuff so far? Do there any questions about things? All right, let me throw one more at you. What is that as a logarithm? The log base 7 of 343 is 3. Yeah. Okay, good. Okay, so what logarithms let us do is find an exponent that we don't know, right? The stuff that we looked at a minute ago, like the equations where like I can kind of guess it, those are exponents that we do know, or we can figure out by just sort of being like clever through it. This helps us find an exponent that we don't know, whether we could find it that way or not, right? Like here, if this was, say this had been 7 to the x equals 343. Well, I don't know, off the top of my head or just by looking at it, the 343 is 7 cubed. Like I don't know that. If you do, that's awesome. But like at some point, like you just don't know all of the things, right? So I don't know that. Now I could find it by just like guessing and hopefully, hoping that it's going to work out. Like 7 times 7 times 7 again. Okay, like maybe that works. Or rewrite it as a logarithm. What would that look like? The second line, the one in purple, what would that look like as a logarithm? The log base 7 of 343 is x. Okay, well, now I've turned this from a like just guess and hope that I can land on it perfectly problem to a, oh, well, if I can do this, the log base 7 of 343, if I can do that, this is a number, right? Now it's like a 10-minute old number that maybe looks a little bit weird and intimidating or whatever, but x equals a number. This is solved, right? Now again, maybe I can simplify that down a little bit further if I can evaluate this logarithm, but like that's done, right? So this again lets us do the kind of thing we were doing a minute ago, but in a way that's a little more like automated, right? Like I don't have to just guess and hope I land right on the number. The logarithm will do it for me. So the question is like, well, okay, how do I evaluate that then? If you take a look at your calculator, somewhere there should be a button that says log, and somewhere there should be a button that says ln. And the shift function of those would be like 10 to the x and e to the x. Log with no base written means the common log or the log base 10. So if we write like the log of 100 with no base written, what that really means is the log base 10 of 100. The reason that we leave the base part off there is that we do everything in base 10, right? Because we have 10 fingers, so we do everything base 10. So this thing is common enough that we just suppress the base part. Like this wasn't my decision, like other people decided this. Probably not just to frighten school children and confuse people, but that's just the way it is. So log with no base written means log base 10. So if you want a calculator, just punch in log button of 100, you should get 2 because 100 is 10 squared, right? Okay, so that's what that means. ln means the natural log or the log with base e. Talked a little bit last time about the fact that in a lot of modeling stuff, especially in like the hard sciences, you know, biology and chemistry and stuff like that, e comes up all over the place. Because of that, it gets its own sort of special name and special reserved thing. That's the ln, which is the natural log or the log base e. So if I write ln of, you know, whatever, that means the log base e of whatever that thing is, right? Natural log, because e is, you know, sort of a weird number, right? Kind of like pi, again, transcendental, long, non-repeating decimal thing. Because of that, the numbers aren't going to be as pretty there generally, right? Like, which is why I can't just write down the ln of some number that I know what the answer is going to be, unless it's just e to a power. Like the ln of e to the 5th, well, that's the log base e, so it's how many e's are in e to the 5th. That would be 5. But those are the two that like every calculator in the entire universe has those built in, because those are the ones that we use the most frequently. Way back, you know, 50, 60 years ago or whatever, instead of well, even hundreds of years ago, instead of a calculator, you had a book with logarithm values and it had these two in it, right? Because they're the ones that are sort of the most valuable in most applications. So how do we do other things? Well, one, we've got this change of base formula. This thing looks a lot scarier than it is. Let's kind of break it down. The log base b of n is the log base a of n on the log base a of b. What this means is that if you want to go from this base to this base, you just take the log of the thing you wanted, divide by the log of the original base. So if I wanted, what was it a minute ago? The log base 7 of 343. I could do that as the log of 343 over the log of 7. The important part is that the one on top and the one on bottom match. So when you change it, you just change to some other thing that you know how to do, right? I don't know, or I don't have a calculator button or whatever for the log base 7, but I do have it for the common log or from the natural log. So you could have done ln here on top and bottom also, or instead. So I just do the log of the thing I wanted in the first place and divide by the log of the original base. And when you do that, you should get 3. Now you may be able to do the log directly. Some graphic calculators will have this built in. If you go to the math menu and on the first thing there, scroll all the way to the bottom. If you see a thing that says log base, that'll let you type in just kind of directly whatever you want. If it's not there, then yours doesn't do it, which is fine. On something like a test, you're gonna need to, you might need to do this once or something, and it might not even show up at all. Because a lot of stuff I'm just gonna ask you for an exact value anyway, so I just don't do the calculator version. But if it's there, that will just let you type in directly, the base that you want and the number that you want to take the log of, right? So you may or may not need the change of base thing. It's kind of nice to know for a couple other things as well, how to do that change of base, but that's how it works. Okay, so how does all of this actually help us? We started all this by talking about solving 5 to the x equals 20. Again, I can't just do it by hand because I don't recognize 20 as a nice power of 5. If I start going through powers of 5, 25, well, we skipped over 20, right? So it's not a nice one that I can do that way. But how would you rewrite that as a logarithm? Yikes. As a logarithm, the log base 5 of 20 equals x. Okay, well, we've solved it. That's the exact value that would solve that thing, right? Let's go ahead and get an approximation for it. So do the log base 5 of 20 in your calculator and get a decimal for it. Again, this would be an exact value. When you go to the calculator, you're getting an approximation. But go ahead and get that and give it to me to like 2 decimal places, maybe. 1.86. Okay, well, the nice power is 5, then 25. Well, we skipped over 20, but 20 is between 1 and 2 then, but ought to be closer to 2, right? So this makes sense as an answer, right? And again, that's rounded to 2 places. Okay. Does everybody kind of have a feel for that? Like, that's cool, right? Like, that's so the logarithm, just this one, like, rewrite this thing like this thing step, like, that does. That's where the magic happens. That's solving the thing. And then, okay, maybe I got to evaluate it, which kind of has its own thing involved. But all right, so hang on to those. There are 6, I guess, problems there at the top of the back that you should now be able to do. Some of them are things that you could do by just kind of, clevering your way through it like we did the stuff earlier, or using the logarithm will sort of do the work for you. But do these for tomorrow. We will sort of quickly go over that and then keep talking about logarithms and how this stuff all works. All right, y'all have a good day. I'll see you tomorrow.